Hi, we are going to continue the lecture about calculating areas and distances, and so this is going to be part 2 of that lecture. You remember that our job was to go ahead and find out area under a curve limited by some straight lines. So here we have a graph of a function, and we are starting at some point A, ending at some point B, using the x-axis itself as the floor of this region, and we attempt to find this area inside this peculiar looking region. Our idea was to cut it up into some strips, approximate these strips as rectangles, and add up the area of all of these rectangles. So we have the job of repetitive addition of something that is calculated by some procedure. We need to have a shorthand for handling these kind of summations, and that is what brings us to the following. So we have something called sigma notation. Sometimes it's talked about as summation convention. To explain it, the best thing to do is to just go ahead and write an example, and then we come back and see what is involved in general. Let's look at the following peculiar mathematical expression. Here's a letter sigma, and now in front of it I write some expression, for example 1 plus I squared, and I write here I equals to 3 to, for example, 7. What is meant by this particular notation? It means that this expression should be evaluated for various values of this so-called index. That index starts at the number 3 and goes in integer steps to 7. Let's go ahead and do that. So those values that are calculated, then they are going to be added. So sigma notation or summation convention refers to the addition of quantities obtained from a certain formula, and the numbers that are going to be substituted for the variable of this formula are written at the bottom and top of this sigma. So if we go ahead, first I will replace I by 3, so that's going to be 1 plus 3 squared. Next we are going to, after 3 is 4, so we write 1 plus 4 squared. After that is 1 plus 5 squared, and 1 plus 6 squared, and 1 plus. That's where we stop. When we reach to this number, that is going to be the end. Now, could you go ahead simplify this in a variety of ways, usually using a calculator to find out the values of the fractions and just adding them up. Just remember, these are ordinary fractions here. For example, this is just 10, and that's going to be 4 squared, 16, and 1 is 17, and this one is 26, and here's 37, and then this one is 50. Typically it doesn't pay to try to take common denominators or anything like that. After this stage, everything is converted to decimal, and you evaluate that. So the idea of the summation convention is to have a shorthand for repetitive summation of something that comes out of a formula. This is referred to as an index. Sometimes referred to as a running index. Sometimes is referred to as a dummy variable. Why dummy variable? You see on the right hand side there is no I really. I is just a placeholder for these numbers, and there is no presence for I here itself. This is called the lower limit of summation. 3 here is the lower limit. 7 is going to be the upper limit of the summation. So in general we are going to have formulas looking some function of I is calculated. I starts at some number, so that's going to be some starting number, whatever starting number is, and going as far as some ending number, whatever that ending number is. So this S and E are just start and end of our calculation. So this thing simply means you start calculating F at S starting point, then you step up one by one, and then you go on, and the very last number that you are going to write is going to be evaluated at whatever the ending number is here. By convention, if the number at the top is less than the number at the bottom, the sum is taken to mean 0. So if somebody for some peculiar reason writes something like I is equal to 5 to 3 of whatever, for example, let's say I over I plus 1, our convention would be if the ending number is smaller than the starting number, this is 0. So we are not going to count backward or anything. If there isn't anything to do after 5, there isn't anything to write, and the summation, empty summation, is defined as 0. So empty summation okay, now let's go ahead and make a summation notation for our area calculation. So we are going to go ahead to our original problem. Original problem was, here you have some function y is equal to f of x. Our desire is to calculate the area from A to B by approximating it with n sub-intervals which are taken to be of equal width. So that's going to be our assumption all the time, that we are going to divide this to certain number of sub-intervals, all of them of the same width, and calculate the areas of each of these rectangles and add them up. Well, we need quite a few pieces of notation here to be able to represent all of our formulas. The situation is going to get rather crowded with all sorts of letters and indices and various lengthy formulas, and it makes it typically intimidating for the students, even though the idea is very simple. Keep in mind that all we are going to do is just practice addition. It so happens that the addition is repetitive and comes out of certain formulas, and we want to come up with a shorthand notation of this style with the sigmas that's going to tell us what we are adding up. So we might as well fasten our seatbelts and be ready for a bit of a messy looking formulas. First of all, these sub-intervals, each of them have a width. For example, if I want to use 5 sub-intervals, I have to take this interval and divide it by 5. The interval itself is b minus a from here to here. Whatever n is, I have to divide this by n to get my width. Now this width is written in one of two notations. Sometimes it is written as delta x, like a difference in x. So these little distances, one notation for them is delta x, Another notation that sometimes they use is traditional notation. Sometimes they refer it to as H. So it's just a tradition of mathematicians to use these letters. You just be aware of it. So sometimes the same thing is called an H. Next, we want to know the markers that gonna be created here. We are starting at A here, and the next point is here, and next point here, and so on. We want to have an easy way of referring to these points. Standard way of naming them is to just use your axis. Our axis was X, and then we use X0 for the very first one, which is just same as A. This point is going to be X1. This point is X2, X3, and so on. The very last point is going to be Xn. For example, in this setup, we have 1, 2, 3, 4, 5, 6 intervals, and this one in this picture is going to be X sub 6. In general, if you use n subintervals, whatever n is, that is going to be labeled as X sub n. Now we are essentially ready to go ahead and write a formula for our left hand rule. So we had the formula for the left hand or left point rule. Let me use that phrase. Left point rule. You remember what that was? Left, we used L for that. We used to put some n under it to indicate how many subintervals we had. Left meant that you make your rectangles at the left side of each of these intervals. So how would you do that? You take the height at the very first point, which is X0, and then this one and this one, and multiply each of them with delta X. So let's go ahead and write it. So the formula was delta X, so that is the width. Then I have to start multiplying by value of the function at the very first point, or you remember what that is? This, you have to multiply by this height. How do you figure out the height? Take the point, plug it in your function, you get your height. This is f of x0. That's how tall this is. And this is f of x1, x2, and so on. So here we are writing f of x0, very first point. F of x1, that would be this height. Okay, that is the next height. And then f of x2, that is this height. Question: when I keep writing these things, what would be the last entry in this list? So I will keep going or keep writing stuff. Question is, what is the last f I'm gonna write? Now do me and yourself a favor. Do think about this couple of minutes. Make sure you understand exactly what is involved, and come back to this and check your guess. Again, question is, what's the last f? F of x. Now here I give you the answer. The last rectangle of this type is this one. Its height is calculated here, not at xn. The one prior to xn, how do you write that? You write it xn minus 1. Whatever your n is, you have to step back 1. So that's going to be n minus 1. That's going to be our formula for ln. Now how about using a summation notation to show the same thing? So delta x. Now here's a repetitive summation. So I say sum the following items. Sum of what? F's that are calculated at x's which are indexed with the index I, with I starting at what? Can you figure that out? What's the starting point? We are going to start at 0. and we are going to end at n minus 1. So these are not the numbers that are used as argument of f, rather these are just indices of x, that's all. Now let's go ahead and write the right point rule. Right point rule, we used Rn for that. Now, can you figure out what happens if you start with at the right point? At the right points, we have the following rectangles. Here I go. The very first rectangle that we are going to build is going to be this rectangle. The second one is this. Third one is this one. Fourth, fifth is the sixth. So what's the very first height I need? Very first height. Did you figure that out? First height is going to be evaluated at x1. What's the last height I need? Last height is the height right at the very last point. That's xn or b. So we go ahead and write this is delta x times, we start at 1, then 2, and so on. Now stop at the very last point. What's the sigma notation for this? That's going to be delta x times the sum of quantities f of xi. Now I ranges from 1 to n. That guy started from 0, ended at n minus 1. This is all shifted 1 unit right. Well, how about midpoint rule? Our picture up there got very crowded, so perhaps we go ahead and draw it again. Let me draw my sub-intervals very big so that we can see them easily. So n typically a very large number, but here we just have 3 segments. So again, this was my x0, this was x1, x2, and so on, and the last one was xn. So that would be xn minus 1 in this problem. N is just 3. Our next formula would be for midpoint rule. Midpoint rule, let's call it MN. What was the idea there? Pick this midpoint, go straight up, make your rectangle here. Here, make the rectangle here, and so on. How do you want to give the address for these midpoints? You have many options. Here, let's review the option. Suppose I want to call this my very first point. Let me call it, say, what's a good letter here? Let's call it, say, T1. The midpoint, you can find it by starting at the left point and going half step to the right. You can start at the second point, go half step to the left, or you can use the first and second and average them if you wish. For example, you can say x0 plus x1 divided by 2. Maybe I should use a different color. Or you could use, say, x0 plus half of delta x. Or you could say x1 minus half of delta x. All sorts of options, whatever is comfortable for you, that's what you use. So if I have this midpoint and the next midpoint, that's going to be x2, and the next midpoint, and so on, the very last midpoint, you see that we labeled it like the point that is sitting on the right of it. So the last midpoint is going to be labeled as Tn. So our formula in this case will be again delta x times value of the function at the very first midpoint and the second midpoint and so on all the way to so for any of these things we could write a formula, but let's first write the summation notation. It's delta x sum of all f of ti's, I ranging from 1 to n. Now don't misunderstand the situation. We are not trying to memorize such formulas. There isn't anything really to memorize. The idea is very simple, straightforward. You're just adding things up either from left or right or middle, so there isn't any big mystery there. You're just learning how to play with this summation notation. So do not get overwhelmed by so many letters being thrown at you. Just go with the flow of all these concepts and notations. Now sometimes you need to a little bit more specific addresses for these x's. How would you go and get the address for individual x? Here is a very simple way to do it. Remember, x0 is just your left point. x0 is same as a. x1, well, one way to go about it is start at a and then take one step. So that's 1 delta x or 1h. x2, if you wish, you can start at a and say I want to take 2 steps. So that is 2 delta x. And then x3, you start at a and then you take 3 steps to get there. So here are these little formulas that can provide for you what these x's are. So here is a big formula. You can write x. If you want to capture any of these, you give a general formula. So you start at left and take as many of these steps. I delta x is going to bring you to whatever x you want. X number I is going to come from this formula. So when you are using xi here, you can use that formula to give us explicit address for the ith point you're going to use. So keep that in mind. Now let's go ahead practice one of these summations. So I say use right point rule. I keep using right point because you're probably more comfortable with counting, starting at 1 and going to n. But left would be just as okay if you start at 0 and end at n minus 1. Most human beings are more comfortable with counting starting at 1, so that's what I keep using. Use a right point rule with n subintervals to find area under f of x is equal to 2x squared plus x over interval from 1 to 3. So here we have some simple function, some parabola or whatever it is. Let's just draw a picture, even though picture is not necessary. So here is some parabola. We are starting at 1 and going as far as, say, 3 is here, and we want to find a summation formula for the area that is enclosed here. So what do we need? First of all, I need my delta x. Delta x is gonna be this total width, which is 2, so that is 3 minus 1 over n, or just 2 over n. Next, I need to know where my point's gonna be. Let me blow this picture up so that so suppose here is 1. Let me go all the way here. Suppose this is 3. So you remember that is going to be our x0, next guy is going to be our x1, next guy is going to be our x2, and so on. What was our formula? Our formula for xi was, we start at the left point, that is, our left point is 1, and we take these many steps, I steps we are going to take. Each step is going to be this wide times 2 over n. So again, what is this? This is what's our a. This is I. This is delta x. So what would be our summation formula? In this case, we said we want to use the right-hand summation. R n is going to be delta x. Maybe I better write the formula we had. R n was delta x times the sum of the function f evaluated at xi, counting from 1 all the way to n. Now our delta x is just 2 over n. Our summation, well, I just write the summation. I is equal to 1 to n. Whatever function I have to apply it to these xi's, which are now written as 1 plus, I simplify this as 2i over n. Who was our f? Our f was given as 2x squared plus x. Let's go ahead. F of x was 2x squared plus x. So if that is the case, what's going to be f of 1 plus 2i over n? All we have to do is to do a bit of substitution. I take this and use it for my x. So I just write 2 times 1 plus 2i over n squared, that is 2x squared portion, plus x, remember that's just x, plus 1 plus 2i over n. That looks rather nasty, but that's just the beginning. We actually have to go and clean this up, open it up, and see what is going to show after all those calculations. I open this up. 2, 1 squared is just 1. You remember squaring identities, right? If you have x plus y squared, you write x squared, I write 2xy, twice the first and second, becomes 4i over n, square of the second. That's going to be 4i squared over n squared. This one is just sitting by itself. 1 plus 2i over n. One more round. 2 times 1 is just 2. 2 times 4 is 8i over n. I have maybe I just step by step, 8i over n, plus here is 8i squared over n squared, plus 1 and then 2i over n. One more round. 2 and a 1 makes 3. 8i and 2i makes 10i. And this guy stays by itself. 8i squared over n squared. That is our f value. What is left? Rn is 2 over n times this sum. So Rn is 2 over n times sum of I starting from 1 through n of, this is my f, this is 3 plus 10i over n plus 8i squared over n squared, whole thing. Is that the end of it? Well, we are halfway. If you bear with me, we can clean this up quite a bit. Let me help you with the cleanup process by doing it piece by piece. Suppose these things were not here. Suppose all I had was just 3. Let's see what's going to happen if I just had 3i from 1 through n. Now that's a strange looking thing because there's no I here. What does that mean? It means for each of those intervals or each of those rectangles you had, add another 3. This simply means 3 plus 3 plus, got into software problem again, plus 3 and so on. How many 3's do we add? There are n intervals. This is n times. So what is that? 3 added to itself n times. Well, that is just 3n. Okay, so this one can be added by itself. Then we go ahead, this portion we add, this portion we are going to add separately, and this portion we are going to add separately because they look so different from each other. We could just break it up. So I go ahead and break that up. This is 2 over n of sum of I from 1 through n of 3. Let me put a big bracket here. Put this guy separately. 10i over n I from 1 through n, and sum of these guys, 8i squared over n squared. Again, I ranges from 1 through n. So what trick have I applied? Here, the writing implies that you add these guys, these 3 things first, and then you add all the contributions from the very first rectangle to the last rectangle. We are changing the order of summation here. We are adding all of these contributions for each of the rectangles, then each of these contributions, then each of these contributions. Why do we do that? Because the way we are treating I is different in each of these things. So we handle it separately. Hopefully that is more understandable. We say 2 over n. This one, we learned what happened. Sum of a bunch of 3's is just 3 times how many times you added them up. So this is just 3n. How about here? Pay close attention that this 10 is a constant. So is this n. For our purpose of summation, this is also a constant. The thing that is changing is I. I is ranging from 1 through n. That is, the very first of these things is 10 over n. Next one is 20 over n. Next one is 30 over n, and so on. Maybe I better write it here so that you are not mystified by this. This is sum of 10i over n. I ranging from 1 through n. What does that mean? It means take I to be 1 first. So all you got is 10 over n. Then take I to be 2. That's 20 over n. Then take I to be 3. This is 30 over n. And so on you go. the last of this, I becomes n itself, and this becomes 10n over n. Well, a reasonable human being is going to add these things like this. Factor 10 over n out of it. This is going to be 1. This is going to be 2. This is going to be 3, all the way through n. So that's why we say in this summation, the multiple like this 10 over n is a constant. You can factor it out and write it all the way out here. So I go ahead and write that 10 over n and continue with my summation. I cleaned up my summation a little bit. All the extras came out. Same game is going to be played here. For our purposes here, 8 over n squared is a constant. I can take it outside, 8 over n squared, and then whatever is left is going to be summation of I squared, I still ranging from 1 to n. Are we there yet? Well, we are going to get there. Let's see. One more round. We have 2 over n. This one is 3n. This was 10 over n. Now, do you remember at the very beginning I asked you guys to keep in mind a couple of formulas? One of them was for sum of all numbers from 1 through n. You remember what that was? Sum of I from 1 to n. What does that mean? Just what we had here, 1 plus 2 plus so on, sum of natural numbers starting from 1 through n. We had a very simple formula for this and simple explanation. Average first and last, and then multiply by the number of pairs. So n over 2 was the number of pairs, n plus first and last is the sum that we had. So the formula for this was n over 2 times n plus 1. Now we go ahead and write. This is 8 over n squared. Do you remember what was this one? If you have sum of I squared, I ranging from 1 to n, what does that mean? Start at 1, square that, and then square 2, square 3, and off you go all the way to n squared. What is that? We had a formula for this. You remember that was n over 6 times n plus 1 times 2n plus 1. That was our formula. So what we are going to do here, this expression is going to be replaced by its equivalent, which was n times n plus 1 times 2n plus 1 over 6. Okay, are we done? Well, we are there almost 90%. We have developed a formula for calculating area under that particular curve over interval from 1 to 3 using n subintervals and the right endpoint rule. Well, what do we want to do with such formulas? The main thing is to let n grow very large and find out what's the limit of that expression. To calculate the limit, we might go ahead and clean this up a little bit so that limit calculations will be easy. How do we clean up? Well, let's see. in this I go ahead and multiply through. 2 times 3 is going to be 6. 6n over n. Obviously n's better get cancelled. 2 over n times, maybe we don't make life hard for ourselves, let's simplify before we multiply. I simplify these two n's, this 2 and 10 I simplify also to 5. So now I have 2 times 5 is 10. I multiply with this parentheses, that's going to be 10n plus 10. I have to divide by this n. Next, what can we simplify here? Perhaps we go ahead and simplify this with that one. So 1 n is taken out from numerator and denominator. I might as well go ahead do a little bit more, like this is going to be 3 and this is going to be 4. Now I'll have, maybe I better write this thing and then simplify it in the next round. 2 times 4, that's going to be 8. N times another n times 3, that is 3n squared. Now I have n plus 1 times 2n plus 1, that we multiplied out n times 2n, that is 2n squared. N times 1, that's n. 2n times 1, that is 2n, and then I have 1. Let's rewrite. Rn became, this simplifies to just 6. This simplifies to 10. This one is just 10 over n. Now I divide, multiply and divide. 8 times 2, that is 16. N squared cancel, that makes 16 over 3. Eight times n over 3n squared, 1n cancels, becomes 8 over let me take my step back, perhaps let me n plus 2n, that would have been less. This is 3n. I simplify this 3 by that 3, this n by one of these n's, and I'll be left with just 8 over n. Is that right? 3n squared and 3n is going to leave me with just 1n, and I have an 8 here. Finally, I have 8 times 1 over 3n squared. I write that 8 over 3n squared. Well, let's put our constants together. I have 16 plus 16 thirds, so this is 16, plus this 16 third, it makes you just multiply it. 16 times 3 is 48, and 16 makes 64 third. 10n and 8n is going to be 18 over n, and then finally I have 8 over 3n squared. We worked through quite a bit of algebra to get to this formula, as simple as they come, as simplified as they come. Of course not simple, but okay. We used the summation notation, we wrote the areas, we used the formulas for the sums of numbers and sums of squares of numbers, we placed them in, cleaned it up, did quite a bit of algebra, and here's the final answer. What is good about this? What's good about it is that, for example, you can take limit if you wish. Limit of Rn, if I let my divisions increase without limit and go to infinity, obviously this goes to 0, that goes to 0, and all that is left is just a 64/3. We just learned that the area under that curve is 64/3. So we had the operation of making the summation, simplifying the summation notation, and then finally taking the limit, finding the actual area. Okay, you will face a couple of questions like this in exercises. Some of them a bit trickier in the sense that they give you this final summation and they ask you to work your way back. Now we are going to talk about one application of all of these things we have been talking about, and that is calculating distance when the velocity is given. Let me make some room here and we start that discussion. There we go. An application of these summation notations or area calculation we just have done is the following. Suppose the velocity of a particle of an object at time t is, so velocity at time t is just simply t squared. The initial position of the particle, how did we show position? S at time 0 is something, initial position, for example, at 5 feet. The initial position is S of 0 is equal to 5. Find the position at any time t, or find the position at time, say, t equal to 1. What does that mean? Position at time 1. What is that? Okay, this is one of those so-called rectilinear motions. Rectilinear motion, we said, means that you are stuck on a straight line, and all you can do is that you can go back and forth on this line. So here's a line, it's like your axis, your road. It has an origin, it has some direction, and you are traveling on this. As you are traveling, as time passes by, your velocity is changing. At the beginning of your trip, your velocity is 0. At 1 second, for example, velocity is 1. At 2 second, velocity is 4. 3 second, velocity is 9, and so on. So your velocity is changing at every moment. Question is, if I knew at time so here's my s-axis. Suppose this is location of 1, 2, 3, 4, 5. When time is equal to 0, I'm sitting here. Maybe I change my 5 to something else so that it doesn't look like an S. I made it worse. Let's go back and change it to say 4. So at time t equal to 0, I am at location 4. I want to wait 1 second. So the particle is going to start moving. At first, it's very slowly moving. Velocity is 0. And for example, if I wait half a second, at half second, velocity is going to be 0.5 squared, it's 0.25, and so on. My question is, at the end of 1 second, and t is equal to 1, where would I be? At t equal to 1, where would I be? Okay, to answer this question, we have to go back to some simple concepts from physics. We need to go and quickly review the concept of speed, distance, and time. What's the relationship between these three quantities? Suppose a distance of two cities 100 miles and you travel from one to the other in 2 hours. What would you say the speed of your vehicle was? You say 100 divided by 2, it makes 50 miles per hour. So the connection between these, speed is distance over time. Well, when you come to university level, take this concept and refine it a little bit. Instead of speed, we talk about velocity. It's a bit more sophisticated. What is velocity? Well, we have the concept of instantaneous and average velocities. But you think about average velocity as a change in position divided by change in time. To write it in notation, you write v for velocity, change in position. If position itself is shown by s as a function of time, change in position is delta s, change in time shown by delta t. How much the position changed and how much the time changed, you divide them and you get the velocity. Well, just like here, that you can cross multiply and write this thing as distance is equal to speed times time. Here you can do the same thing. You can write change in position is equal to velocity v times change in time. So if you are looking at this object in any short interval of time, you want to know how much it's going to travel in that interval of time, you simply multiply the velocity by length of time and you find out how much the particle is going to move ahead. Well, let's go ahead and look at this thing in a picture, see if we can find a connection between this and the area. You remember at the very beginning we said, we gave an example, the velocity of this object as a function of time is v equal to t squared. So here I write t for the time axis and v for the velocity. I'm taking a look at this function, v is equal to t squared. Let's go ahead and graph this thing. Suppose this is v is equal to t squared. Now on this picture, let's go ahead and show delta t times v. Delta t is going to be an interval of time here on the time axis. What is v? V is just the height of this curve. V is the function that gives you the velocity. So wherever you like to draw it, that's fine. Here, suppose this is v. What is v times delta t? v times delta t is the area of that rectangle. The area of that little rectangle is equal to the change in position. In the next time interval, the particle is going to travel, and the change in its position is going to be equal to the area drawn in this strip. And in the next delta t, again, the time that is going to be spent is delta t, in the change in position is going to be equal to the area of this strip. That v, for example, is some intermediate velocity times delta t is same as the area of this. So if we are waiting to see where the particle is going to be, and time has elapsed from time 0 to time 1, the change in the position of the particle is going to be equal to the total change implied by all these little changes. And all of these, each of them is equal to the area of that strip. So the total change in the position of the particle is equal to the area under this function over the time that was given to us. That is, from time 0 to time t equal to 1, the particle is going to move by as much as the area of this region. Well, at the very beginning of this lecture, we went ahead and found what that area is going to be. It feels like a month ago, but it was just an hour ago. We went ahead and found out this area. That area turned out to be 1/3. So that means the total displacement in the position of the particle is just going to be 1/3. Let me write this fact in general. If or let me first finish up the problem. The question is, where would the particle be after time t equal to 1? It's just going to move by 1/3. So it's going to come just a tiny bit further. The final position is going to be 4, which was the original position, and it's going to move by as much as 1/3. So the final position is 13/3. That's right. S at time 1 is equal to 13/3. Now, let me write this fact that we found in general. If the velocity of an object is v of t and its position is s of t, then the change in position during the time interval t going from t equal to a to t equal to b is the change in the position, which is s of b minus s of a, is equal to the area of the function v of t over interval from a to b. So that's an important fact we discovered right now. Change in position is equal to the area of velocity function over the time interval. So here what we actually did our velocity function was t squared. Time interval was from 0 to 1. From 0 to 1, area was 1/3. So the change in position is going to be 1/3. So the particle is going to start at 4 and it's going to end at 4 plus 1/3, which is just 13/3. So we found out the final position of the particle to be 14/3 here. Okay, now that was a bit of a tricky discussion and lecture. So you might want to go ahead and finish up the problems of this section and get ready for the next one. You might want to read through the section in the text. The problems in this section are very much relevant to students in engineering. Anybody who wants to understand the concept of velocity and position is strongly encouraged to make sure problems in this section are done carefully and correctly. Okay, good luck and God bless.